Khalid, please. शुरू करो.
Can you hear me, sir?
Yes. Yes, sir.
Is the screen visible?
Yes, sir.
Okay. Without a further ado, because my time has been reduced from 1 hour to 30 minutes, क्या कर सकते हैं कि जहाँ पर गुरुदेव का इंस्ट्रक्शन हो तो वहाँ पे हम सिर्फ आज्ञाकारी ही बन सकते हैं. First of all, I would like to thank Professor Maharshi for introducing me in this conference. Wherever he goes, wherever he presents his lectures, I myself feel blessed that he introduced me here. मैं उनका शिष्य भी हूँ, उनका भाई भी हूँ, दोस्त भी हूँ, ये उनका आशीर्वाद है. So without a further ado, I would like to move on. That I'm going to talk about today about piezo-plasmon phototronics. This is just a combination of plasmonics with the piezotronic materials. We know very well that BiF3O3 is a piezoelectric material which has excellent piezoelectric as well as ferroelectric properties. So it's just a combination of plasmonic interaction with this material, and we wanted to sort out certain problems. One of the major problems we witness in the present area is that we don't have pure clean energy. And even though we try to get it through the solar cell fabrication, we have environmental disaster. And that environmental disaster is happening through many ways. One of the ways is that we have a discharge of toxic synthetic dyes, and minute contamination, even the minute traces of these dyes are being found in water. That's very harmful to our health because these are carcinogenic materials which can mutate our genetics, and we have many different health issues. These materials are very, soluble in water. They are stable, and they can be easily, remain in water for a longer period of time. So the question is how we can remove these kind of materials. Before I will move on to that part, let me go into the first. Let me discuss what exactly is plasmonics. So when we are talking about a plasma, we can simply regard it as a quantum of ionics, like it's a density of wave which is emerging from an electron gas. We have a free electron which vibrates in metal, and when we apply a certain kind of an electric field in the material, especially to the metal surface, it forms a kind of a dipole that the positive and negative charges get separated. And once we try to analyze this problem through classical model, what we observe is that these electrical parts, that's the negative charges get separated to one end and the positive to another end. When we remove this electric field, these charges try to repel. So, for example, electron repelling is there, but yet they try to combine because of the positive attraction, and that attraction of going together that leaves some kind of energy, and that energy is lost in the form of a damping or the heat in the material. But that's what we here have, that we call it the oscillation of the charges. That's the wave, electromagnetic wave, or the plasmonic factor, and the resonance of these waves with the incident light. If we put on the surface of the material, that incident light and the frequency of the resonance of these charges, if they resonate, we get an effect which we call surface plasmon resonance. This can be quantized effect in materials. But before I will go to in detailing of this plasmonic effectors, let me just move very quickly that these effectors are visualized in nanomaterials, and they help us in further enhancement of photocatalytic effectors or isophotocatalytic effectors or any other effectors. These effectors can be, understood with few examples, such as we have localized SPR, we have surface plasmon. SPRs are surface plasmon or localized. What we have to do is here we need to understand that the frequency that electron gas has, which is oscillating violently, this resonant frequency increases with the electron density. Since the restoring force is proportional to the dispersive charge, which is analogous to the kind of a force constant in a spring, similar to that oscillation, we have that oscillation in plasmons. So here is in the diagram you can see as EELS electron spectroscopy, where we see how the damping is happening at the first peak when the incident light is there, and then this goes on and slowly dies away. Due to the shortage of time, I'm moving fast. I cannot go into the detail. But however, I will show some of the applications that what the plasmonics can have. But since these are moving with the speed of almost comparable to the speed of light, and not to the completely speed of light, but comparable. So what is happening that it will revolutionize our computers and smartphones in the data transfer. So that is one of the major achievements we can have if we look into the fiber optics. That's the conventional phenomenon nowadays being used, and these plasmonics, which will help us in further integration of designing of biosensors, in designing of methodologies to treat the cancers in health sector. This will also help us in designing certain kind of materials which will help us to boost the solar energy. So I'm not going to talk about the other application. I will talk about specifically the solar energy part. I will talk some of the important research which we have recently issued using the SPR based materials. One of the examples, immediate examples can be seen here, that when the plasmon effect is being visualized, that here you see the green is being reflected while the red is being transmitted, and it's the same material, same glass, same Rome. It's a white cross cup in Rome. It's just a beautiful thing which we can visualize with the effect of light, where the green is reflected but the red is transmitted. So here we have that we can work on two parts by having this image, that we have the transmittance or the absorbance, or we have the reflectance. The reflectivity cutoff of the plasma can be used for energy saving windows, which can be done through the coating of the materials, and the reflective part can be reflected into thermal radiation back into the heated room where we need it. So this phenomenon can be used in the solar cells, where we can cut certain part and use a certain part, because there when we have the solar radiations on a solar panel, we need the visible spectrum. Although there is a visible spectrum, there is also the thermal heating, and that thermal heating needs to be avoided before it gets, converted into some form of energy which will damage our solar spectrum or the conversion of the energy process. So there we use some kind of a coating, and this is simply a methodology we can use the transmittance part or absorbance part, and we can cut out the reflective part by using certain doped semiconductors such as indium titanium oxide, tin oxide, and these kind of materials are being nowadays used as an electrode materials in solar panels and also in LCD screens. And we can see that in the earlier ages we were using that tube screens and they were getting heat up, and nowadays in LCDs we don't see such kind of heating process happening. However, we face a different problem that how we can combine optoelectronics with plasmonics, where one has to convert the light which is as a photon into the plasma, this is not simple phenomenon. If you consider as a bulk plasmons, they oscillate longitudinally, whereas the light, the photons, they go in a transverse perpendicular direction to the propagation of light. So the combination of the longitudinal and the transverse is not possible. So we have to combine these. So how is it going to be possible? In a surface plasmon, which is transverse, but they are mismatching to photons in their momentum. So the two energy values or curves never cross each other. So we have to find some way, and that is only happening by providing that necessary momentum through the grating, which transfers the wave vector k equal to 2 pi over d, where the d is the line spacing between the gratings. Here you can see there is another way to combine these two phenomena is by attenuation of the total reflection. So here what we do is the coupling of the photon with the surface plasma using the attenuation or the total reflection at a metal coated glass surface. The exponentially dampened light wave escaping from the glass can be matched to a surface plasma or the thin film in the metal coating. This technique is very surface sensitive and can be used for biosensor applications for detection of any kind of disease or vitamins or other things. However, as I mentioned in my earlier seconds, that we are going to talk about this phenomena applicable in the solar cells. As you see that there's a lot of light coming to the deserts like Saudi Arabia, while it is not that much in Europe, but it is somewhere good in Asia, in a country like India. So there is a winter, there is summer, but we can use this light source, which is a blessing, and we can convert it into energy, and which is happening. But however, we need to have and design certain kind of solar panels which can produce best and efficient solar conversion into the energy sector. So in that case, what we see, solar electricity is still currently about 5 times the cost of the coal generated. 50% of the cost of the solar module is the cost of the silicon wafers, which are 300 micrometer thick. This can be reduced with thin films, which could be 2 micrometer thick. So we need to improvise that the thickness of the surface, which can be 2 micrometer, and that thickness is not only the challenge. We need to find out a material which is not tearable, which is not breakable, which is going to support the plasmonic interaction to increase the photocatalytic efficiency. So in this case, there are some of these examples that one way to improve the method is to minimize the amount of light reflected from the cell or transferred through it, since this energy is still being lost. The conventional approach is to use an anti-reflection coating on the surface, but there is again a problem. While these coatings are good at preventing reflections, they cannot stop light being transmitted. In some cases, almost half of the light passes straight through it. So that's one of the issues, that the transmitters should be there. And when you look at the visible UV spectrum, it is huge. We have a certain material that some of the wavelengths are being absorbed and some of the wavelengths are being ignored, or we can say they are being transmitted and they are not being absorbed. So we need to find out a composite material which absorbs the complete wavelengths, and that's a challenge, and that is still going on. And how this could be done with certain techniques, such as we can have the photovoltaic cells which have light trapping properties, like some of the cells are being formed which have the vapor cells which can be acting as a trapping centers by changing their geometry and their geometry helps us in the optical absorption. But still, we see that it is not that kind of a thing which helps us in increasing the photochemical activity. So what we need is that the surface, whole of the surface, should be some kind of absorbent, and that's only happening through some surface plasmon interaction. So moving to that surface plasmons could be localized, where we have a dipole or multiple oscillations of the electrons, or the surface plasmons, they can be that they are bound to the interface, where they are propagating as the whole of the surface is being covered in this phenomenon. Both types of the plasmons can be used to enhance absorption in solar cells. So it depends upon what kind of choice of material we have used, which uses the localized or which uses the surface effect. So this is just how the localized plasmons can be and other things. So let me go directly to the part which we have which we are going to be right now in discussion. What we design, we have BF. BFO is a piezoelectric material which has got good ferroelectric properties. So we want to use these piezoelectric properties and ferroelectric properties, but we want to combine this material with some kind of a material which has the plasmonic effect, and that is a noble material like gold. So we are functionalizing BFO material with the gold nanoparticles. So these combinations were done with the hydrothermal process, and the material which we found was analyzed through X-ray diffraction, where we had that the BFO had a good rhodohedral structure without any impurity phase. However, we noticed that there is a gold presence which was evident by the peaks at 38 degree and also at 47 degree, which is reflected in the Miller indices peaks of 111 and 200. There was no separate distorted peaks to some impurities which we usually have in bismuth ferrite, or we have iron oxide alpha Fe2O3. That's not present here. So after we analyzed what we actually wanted, we wanted to have a photocatalytic technology where we can use this material to increase the photocatalytic activity and to demonstrate that this photocatalytic activity process of BFO material has high efficiency in order to absorb the visible region of the sunlight, which increases the recombination rate of the photogenerated carriers, thereby significantly it suppresses the practical realization of effective photocatalysis with the combination of a piezoelectric process and ferroelectric process of BFO. So it is just to design a photoelectrochemical method where we have two types of electrodes, which could be the N-type and the P-type, depending upon what type of material we are combining. Since you know that BFO, it has a wide, narrow band gap of 2.1 to 2.7 electron volt, and it is very excellent material, it is very cost effective, and we need to play around this material and combine it with some surface plasmon effective material, which is gold definitely, and it helped us in a way that by looking at how this material can be used in the production of one photocatalytic activity, which is going to help in the solar energy generation, also by using this photocatalytic process in the production of hydrogen. So hydrogen is one of the things which we need nowadays, rather than other conventional methods where we can have a more energy process. So hydrogen production was used to determine the efficiency of this material. By looking at this X-ray spectra, we wanted to make sure that this material is pure. There is no impurity coming from any other material. So we have this different binding energies of 4F state of bismuth and iron 2P state, and we have the pristine BFO in every case, and with the gold decoration on the surface of the BFO, that too was visualized, and we see that each of the material has its own peak. There was no attribution of any kind of impurity phases, and we had the certain satellite peaks which we feel that it is because of the BFO interaction with the gold. Due to that, it has emerged. Looking at the morphological images of these materials, we see that these have something like a sea urchin like 3D structures from the SEM image, and these images, the A and B are the SEM images, while as the C and D are the TEM transmission electron microscopy of these images. We see that in the first part, which is a 5 micrometer, but when we see the deeper measurement, we have gone by taking the TEM, which are that the gold decoration has taken place somewhere around the edges, and which is 50 nanometer wide, and while the edges were somewhere around 5 nanometers, and which could be reflected also in the image F in the picture. We performed that UV visible spectra of these materials, and to understand that whether there is SPR is possible in this material or not, we had a broad absorption of these peaks. Well, we see that BFO, pure pristine material, has a broad peak, but there is no SPR type of thing happening in this, whereas when we had this different doping. What you might be very much confused that what is AU1 and AU2 and AU2. This is actually that we have kept the concentration of the gold as 10%, 20%, and 30% in these materials. So based on that, we have made the classification of sample 1, 2, and 3. We see that as the doping concentration of the gold is increasing, that the surface plasma resonance process is having much better emergence, and we see a sharp peak happening between 600, almost near about 620. We performed that the photoluminescence process, which shows that the punching of the photoluminescence punching is happening, and which is approximately an opposite of the absorption, what we see in the visible spectrum, which is quite evident. And when we further went to see whether this kind of a material is good for anything like solar process or photocatalytic, we saw that we actually in this process what we did, we had the photo process in the presence of dark and the presence of the light. However, since I said in the beginning that we combined the process of the piezo-photoelectric, what we did, we kept the sonicator material on the sonicator bar, where we provided them some kind of shape to have this piezoelectric effect. So we combined the piezoelectric effect in the dark and in the light, and then we perform simply without the sonication the process in the light and in the dark. But then we combine both the process, that the light and darkness should be with the help of piezoelectric process also, by providing the sonication. To a certain degree of angle, the illumination was the maximum. So what we got, that we had this linear sweep volt geometry at different potentials around 0.8 volts. Although you can see the window of the measurement was 1 volt, at the 0.8 we had almost 22%, 22 microampere per centimeter square the current generation, and that was highest achieved for the gold light, BFO light that was, while as in the dark there was, but at 0. When considering at the 0.8 window, we had almost 22 microampere current. And since we had done this measurement, we also went for to check for the how this process is going to work for on and off state using the current with versus the time. And as the time, we see that the time period is increasing from 200 to up to 240 seconds to see the cyclic performance of the material. Is it going to be repeatable, or it's going to degrade with the progress of time in an on and off mode? We see that for the off mode, the maximum time was current density was achieved as 10, while as for the on mode it was 24, which was again for the gold decorated BFO. Looking at the impedance properties, it's very important to understand while doing these photochemical measurements or solar cell measurements, how these materials are being very effective when we see their current processes. So the impedance spectroscopy gives us one of the ideas that these materials are somewhere good or bad if the impedance is high or low, determining that the capability of the material. So as you see that BFO with the decorated with the gold has the impedance peak which is lesser compared to the pure BFO, which is quite evident, again giving us through the Nyquist plot that we have this question of higher gold concentration is good in photochemical process. As we in the beginning, I discussed that it is not only the photocatalytic process to have the splitting of water and to generation of hydrogen or the absorption of the light to generate the electricity. It's also important to see how these kind of materials can be helpful in removal of the synthetic dyes which are available in the water, which are very dangerous for human civilization. So that we have the different materials where we tried how this degradation process could be more better. So with the use of the orange blue dye, we see in the methylene dye that the efficiency of removal was almost 98% achieved in methylene blue dye. And we used also the chlorophenol, which was also there, and the Congo red dye, and the efficiencies you can see that, but methylene blue was the highest degradation efficiency shown material. When we see with respect to the piezo phototronic and simply photocatalytic process, as I mentioned that we had just the piezo process and the photocatalytic process and the combination of the two in different time scales and in different conditions like dark and light mode. Here you can see that piezo pyrolysis model, which is purely just for the pure BFO, and while as we have the piezo photocatalytic, both the processes. The mechanism is showing us that the testing condition for the BFO testing generated 180 micromole hydrogen. This is the concentration versus the time, and what we did, we had put the material into the chamber where we had an argon atmosphere by evacuating first the whole of the oxygen on the whatever was there. We created the vacuum, but then we had an argon environment. Then as the process of the reaction was taking place, then with the help of a hematoid syringe, we just took periodically the gases which were evaluated there, and then we, through the gas chromatography, we just measured how much the gas was generated, and with the concentration versus the time, we see that in the pure BFO testing, 180 micromole per hour of hydrogen molecules were produced, while as in the gold decorated, we see that 470 micromole for the concentration 10 and 219 mole for the concentration 20% and for 320 micromole for the gold concentration having 30% was achieved. And in the photocatalysis, we have noticed that hydrogen generation of 300 micromoles was there, 300 micromoles per hour for pure BFO and 420 micromole per hour for 10% gold, 460 micromole for 20% and 510 micromole per hour for 30% gold was noted. However, you can see that when we see that is this process of photocatalytic and piezo-photoelectronic, the combination process, which one is more helpful? We see the highest produced hydrogen value of BFO AU3, which is several times, almost 1500 times higher than the pure BFO, where there is only piezo-catalytic process happening and the production of hydrogen is taking place. We have chosen, in fact, methanol based on its low carbon chain length, since the carbon chain has the hydrogen presence, so it could be, if we choose a different kind of a material, that the hydrogen process is happening to other breaking of the bonds in this organic material. So we choose this methanol with the intention that the hydrogen number is here less. This enormously enhanced hydrogen generation, which was synergetic effect arising from this process. We saw that recyclability of the hydrogen projection with the BFO AU gold is better compared to other materials, and it has shown in the second and third cyclic efficiency 93% and 85%. So that was one of the parts we achieved, and in the second part, what we tried to do is that we had dye-synthesized solar cell. In the first one, it was not dye-synthesized solar cell, it was just a BFO combined with the gold process. Here we have the dye-synthesized solar cell. We doped with the material BFO with the gadolinium, and again we decorated this material with the gold. And I'm not going to discuss the process of this, and you can see that there's a citation. You can go to the paper and you can see how the fabrication process was done. Whereas, again, when we had this X-ray diffraction pattern, we saw the gadolinium is there, the gold is there, and there is two. In the second part, you can see there are some, peaks, which are impurity peaks, but we have the pure bismuth gadolinium. And those impurity peaks which we see as a star are not actually that we have a different kind of a crystallographic structure. It is just the gold is present here. Gold presence is there. So again, you see that we have this XPS, we try to see that how the process is happening. Is there any impurity phase? We saw that the gold is there, gadolinium is there. This is the SEM images, and this is the transmission electron microscopy. In the SEM, we see that gadolinium and gold, they are all uniformly distributed on the surface of the niche material. And with the catalytic process, we try to change, the pH value. We saw how the pH value is affecting on these switches, and as the pH value of 10, we see that we are going towards the negative side, that's the N-type of semiconductor based photoelectronic materials. With the gold decoration, again we see when we have the decoration of the gold on the BFO surface, we saw that the effect of the gold as well as the gadolinium is there. And but we see that as the prominent phenomena here is that is it possible that the piezoelectric process can be combined with this plasmonic effect? Yes. that the gold has enhanced the photocatalytic process, and it has enhanced the piezophotonic process of this material, which can be seen by having a look on the STR, and the photoluminescence also again shows that the peak is dying. And this is the different pH values we have taken. Since we have used it as a dye, for the dye here, we have chosen a tetracycline, which is also as a antibiotic, and we use the different dosages of it. And again, we see that as the percentage of the pH value is increasing, the degradation process with the time and the production of the hydrogen is increasing with these materials. These were some of the photocatalysis versus piezo-photocatalysis processes which we tried to combine, and we saw that the gold basic material and the highest percentage of the gadolinium was 5%, which showed the most efficient phenomena in these materials. And we also tried the IPC efficiency measurements of these materials, and we got that the gold basic phenomena has the highest percentage, which has achieved almost around 42% with the within the range of the spectrum of the visible light. We saw the current density phenomena also, which again showed that with the 5% efficiency and the gold decoration, it has the highest possible piezo photocatalytic phenomena. And this is the third process in the continuation of this work which we have done. However, I will not go into the detail. Here I will mention only what was the difference between the earlier one and this work, that here we used a different method, that is we prepared the material with the help of green synthesis using the plant extract. And with that plant extract, which helped further us with the absorption of the visible structure, and we had some kind of a beautiful efficiency compared to the earlier one. And here you can see we have almost a process at a 0.8, almost 24%, 24 microampere per centimeter square current, which was earlier only 22. So efficiency was increased with the help of this kind of process. So it was one of the projects which was funded by the government of Saudi Arabia, by the Ministry of Education, to see how we can design the different kinds of solar cells, and that is it possible that we can have increase in efficiency of the solar cells. And we saw that with the gold decorated vehicle, the efficiency percentage was increased compared to the pristine one, 6.8%. And I'm very thankful to you all for giving me a chance to present my work. Thank you very much for listening.
So, thank you, Khalid. Thank you very much that you accept our invitation, and I'm really, the way you presented your work, that is very well. You know, this is emerging area in the field of green energy. I can understand the work you present here. Chief guest is here, head of the institution of the where this conference is going on. He is also here. All invited speaker, faculty members, research scholars are here, and I think due to communication ecosystem, so on the part of entire conference team, I really pay my regards and thanks the way you presented your work. And I know that the use of the BFO, it is very important in the field of solar technology, which is the challenge, which is the major challenge at the present time. I think yesterday there was also one talk where he mentioned about the challenges in solar technology, but I think today's your talk, I think all young people, they will understand. And I think I am sorry that it is difficult for us to choose some few questions, but because of ecosystem, I will pass all the delegates your email and WhatsApp. So if they have any queries, they will contact you by WhatsApp message. Is it okay for you?
Definitely, sir.
Yeah.
We have to answer them any kind of
Yeah. 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 Yes, yes, yes. And and again, your memento I will receive from the principal, your memento, your loving affection from the DAV institution, and I will keep with me when you come to India, so and visit to Shimla, then we will have, celebration on that memento, because these are all, unique occasions which we meet and discuss. Yeah, thank you. So thank you very much. Thank you very much. Thank you. Okay. Thank you. Bye.
So that was